So you guys can see that okay?
Yeah.
Yep.
Great. Okay, I guess this is a good time to start. I feel a sneeze coming on. Whew. All right, so the plan for today is to discuss the Dirac equation, continue our discussion of the Dirac equation, and this allows us to derive the spin, the origin of the spin magnetic moment, and the G factor for an electron. We can derive it using this very simple idea. So let's remind ourselves what Dirac was talking about, and so let's put ourselves back in the shoes of 1928. And so what happened is that we want to combine. The whole point is to combine special relativity and quantum mechanics. And so then what we need is time and space to be on the same footing. And so so to create quantum mechanics that works, then we know that this is what we want. And basically we're sort of what I'm doing is I'm trying to recreate the thought process of Dirac back in 1928. Like, this is how he was thinking. And so what we want is this. We want a Schrodinger equation, right? But we know that this energy is gonna turn, in the Schrodinger equation, this energy turns into IH bar, a time derivative, a single time derivative. And so then this Hamiltonian, whatever the hell it is, we don't know what it is yet, we need it to be proportional. Since this is only a single time derivative, then we need this to be proportional to a single spatial derivative, right? Because we need them to be on the same footing. So, so we need a single spatial derivative. So what Dirac said is, well, he said, well, look, in quantum mechanics, we have the momentum operator is equal to h bar over I ddx, right? And we like that, single derivative, single spatial derivative. So if I have a single time derivative on the left and I want a single spatial derivative on the right, then that means that the Hamiltonian has to be proportional to what? Tell me.
Momentum.
That's right. That's it. That's the whole thing, that's the whole thing right there. That's the central concept. It's so simple. And so that means that we need our Hamiltonian to go like this. We need it to be linear in momentum. So it'll be like some constant times momentum plus some other constant. So that's the form. So this is the form that we want. And so to get all the units correct and to make it in the most general way, what Dirac said was, let's let H equal C times alpha dot P plus beta mc squared. And it's really just a constant times the momentum plus another constant. But the thing is that he said that, well, alpha and beta, let's keep these as general operators. And so this is where his intelligence came in. This is where his genius was, is to figure out what alpha and beta are. Let's keep them as the most general operators, and then let's find out, what are they? That's the whole question. What are these alpha and beta? And so what Dirac did was he said, well, I want E psi is equal to H psi. And so if E psi equals to H psi, then I know that if I just do it twice, if I just hit the Hamiltonian twice, I get H squared is equal to E squared. All right, that's nothing fancy. You've all done that before. But E squared, we know, is in relativity, E squared is just P squared C squared plus M squared C to the fourth. That's just, E equals MC squared formula that you all know. And H squared is just the Hamiltonian squared, which is C alpha dot P plus beta MC squared. And so then when you equate these things from this little equation up here, then you get a bunch of algebra that we did last time, and I certainly won't recreate that. Then what you find is that you find what you do is you get this equation leads to constraints, many constraints on alpha and beta, and then you can find the simplest alpha and beta that satisfy these constraints is as follows. The simplest alpha and beta is that you have to have, and this was some tricky math, but you must have, let's write it down. Alpha is equal to alpha x hat plus alpha y, y hat plus alpha z hat. And what we find is that alpha x is equal to 0 sigma x 0, alpha y is equal to 0 sigma y 0, alpha z is equal to 0 sigma z 0, and beta is equal to let's get this right. Beta is equal to I 0 0 I, where I have sigma x is equal to 0 1 1 0, sigma y is equal to 0 minus I 0, sigma z is equal to 1 0 0 minus 1.
Oh, Professor?
Yeah.
I think the second I in the beta matrix is negative. Is that
Yeah,
true?
that's good. Good, thanks. And so I is equal to 1 0 0 1. Where these are then, of course, the Pauli spin, what we now call the Pauli spin matrices. Okay, and so this is kind of a compact notation because this is, you see that this is actually, these are 4 by 4 matrices. But nobody likes to write out a 4 by 4 matrices, it's too much writing. And so we use this more compact notation. Compact notation. And using this compact notation, we could even say this. We could even say, you see this, we have alpha is equal to alpha x hat plus alpha y hat plus alpha z hat. But we could even write this like this. We could write it as 0 sigma vector 0, right? So this is like a very compact, even more compact notation. And so these, obviously these compact notations have been developed because nobody likes to write all this stuff out. But if it's the first time you've seen it, it's a little confusing, because you're not used to this kind of notation where we're compactifying these matrices. But it's a very simple notation and kind of obvious once you think about it. Okay, so so this is so alpha. So what we have then is H is equal to C alpha dot P plus beta MC squared, and we see that this is and this is alpha here, right? And so this is a 4 by 4 matrix. It's actually 3, X, Y, and Z directions. And so what we have then is, we see that the Hamiltonian then it lives in this 4x4 matrix. And so then what we have is H psi equals E psi only makes sense if psi is a four vector, a 4-dimensional vector. And this is not the famous 4 vector of special relativity. This is a different 4-dimensional vector. So this is a 4-dimensional state. But what are the dimensions? What do these 4 components mean? It's not obvious. It's not obvious at all. What do the 4 components mean? It's a big question mark. Dirac did not know. He just did the math. You see, this just falls out of the math. So this is something that you could derive using, this is just using undergraduate mathematical reasoning. You just come to this inescapable conclusion. This all just comes from this very simple initial assumption, which is this all just comes from the fact that we have H proportional to momentum. And by doing that, then you come to this inescapable conclusion that the wave function has to have these 4 dimensions. But what are they? It's not obvious at all. So I just want you to kind of see, to follow, you know, this is sort of very abstract, but it's sort of simple in a way, but it's just like you're just following the reasoning. And so to figure out what those 4 dimensions are, let's continue, let's keep going. And so the simplest thing to do is to, the simplest way to understand what those 4 dimensions are is to solve the Dirac equation. Let's do it, let's solve it. Solve the Dirac equation, and then that gives you insight into what those 4 dimensions actually mean. Okay, and of course I already mentioned last time what they mean. It's going to be positive and negative energy solutions of spin up and spin down. That's what those 4 dimensions are going to give us. But let's derive it. Let's see. Let's actually figure that out. So let's solve the Dirac equation for a free particle and see what it gives us. So what we have then is we have C times alpha dot P, where P, of course, is the operator, right? H bar over I del plus beta mc squared. So that's the Hamiltonian. And times psi. And psi, of course, has these 4 components. We don't even know what they are yet, but we know there's got to be 4 because beta and alpha are 4-dimensional matrices, 4x4 matrices. And so this is the Dirac equation that we've derived. We derived this whole thing. Okay, so that's what we have. H psi equals E psi, and now let's solve this sucker. So to solve it, let's make an assumption. Let's make an assumption on the form of the solution. So let's do this. Let's assume that psi, and psi is actually this 4 vector, so I'm going to call that, the compact notation is it'll be like a vector, a 4-dimensional vector. Psi, the wave function, which is now a 4-dimensional vector, let's assume that it has this form, some kind of factors. We don't even know what they are yet, but we'll call them A1, A2, A3, A4, and let's multiply the whole thing times a plane wave. Because we know that free particles are plane waves, right? And so so this motivates this type of solution. So let's assume this form, and once we have this form, what do you think we're going to do next? What are we going to do next? Yeah?
Plug it in and then try to find out what A1, A2, A3, and A4 are.
Yes, exactly. What you always do. That's exactly right. So assume this form and then plug it in. That's exactly right. So we're going to plug it in to the Dirac equation. And when we do that, we're going to get this. What's going to happen is this, you notice that the h bar over I del is going to act on the spatial part. We're going to assume that A1 through A4 there's no spatial part. This is the spatial part is here, and this is not spatial. So the A1 through A4 is not the spatial part, but the e to the I k dot r is the spatial part. So when h bar over I psi hits this, then what we're going to get, actually, let me write this. Let me ask you what we're going to get. When that hits this, what is that going to equal? What is this operator going to turn into? Tell me.
It wouldn't just turn into h bar times magnitude of k, or h bar times k.
That's exactly right. That's exactly right. So you can see that the math is kind of simple. That's right. And h bar k, what are we going to call h bar k? What's another word for h bar k?
Momentum.
Yes, we can call that momentum. And so this operator is going to turn into P equals h bar k. Okay? And so what that means then is that our equation, once we plug in our solution, this complicated equation, what I can do is I can rearrange the equation. It's going to look like this. It'll turn into this. I can rearrange it to this. E dot the E times the, this will be the 4x4 identity matrix minus C times P dot alpha plus beta MC squared times A1, A2, A3, A4 equals 0. Because I just divided out the e to the I k dot r. Okay? And that's not hard. It's just a couple lines of algebra. I just skipped a couple lines of algebra, but you can see how when you plug that in there, the del turns into a k, and then I can just divide out the plane wave and just rearrange the terms to get this. Does that look okay to you guys? All right. And you got to remember this alpha is a very complicated object. Alpha is this weird zero. This it's this 4x4 matrix vector thing. It's a pretty complicated object, but it's not hard. It's not hard to understand. It's just sort of tedious. Okay, so we got this. So this is our Dirac equation, and so now we have to solve it. And so now what we can do is we can plug in I, the identity, and alpha, and the 4x4 matrix, and beta, plug them all in, like expand this out. Do the algebra, plug in these 4x4 matrices, rearrange everything, and do all that matrix algebra, which is not hard, but it's tedious. I'm not going to write it all out. And when you do that, this is what you get. You get this thing. You get a 4x4 matrix. You get some 4x4 matrix times A1, A2, A3, A4 equals 0. All right? And let's write out what that matrix is. And this is not hard, just a bunch of tedious algebra. You're just plugging in those 4x4 matrices and multiplying it all out. You can do it. And I suggest that you do it. Go do it. Because it's really pretty amazing what you get in the end. And this is what you get. E minus mc squared is the first component. Then it'll be 0. Then minus c pz minus c px minus I py 0 E minus mc squared minus c px I py c pz. Then the next one will be minus c pz minus c px minus I py e plus mc squared. Just a bunch of tedious algebra, but it's all pretty simple, just tedious. And then here it'll be minus c px plus I py c pz 0 e plus mc squared. Okay, so that's what you get. It's not hard to get that. So it's a 4x4 matrix times that a1 vector, that a vector. And so what do you think we do now? And you guys have all done this a million times. What do we do next? I got a matrix times a vector equals 0. What do I do next?
Find the eigenvalues.
Yes, how do I do that?
Take the determinant with the minus alphas or whatever you want to call the things along the diagonal. And set the determinant equal to 0.
That's right. That's exactly right. Because the thing is, we know that a matrix times a vector equals 0. If that's true, then we know the determinant of the matrix equals 0. That's right. So then what we'll do is that set the determinant of this matrix equal to 0. Okay? And that's not hard either. It's a 4x4 matrix. Just do the determinant. Blah, 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 blah. All the algebra. I'm not going to do it. It's just way too tedious. But it's not hard. So go do it and set it equal to 0. And then you're going to get, and that gets you the eigenvalues. And the eigenvalues are the energies, right? That's what we're trying to get, the energies. And so you get the eigenvalues. And what you're going to get when you do all that, you're going to end up with, you're going to get this. It's going to become, you're going to get this equation. It's all going to reduce to this. It reduces to this. E squared minus m squared c to the 4th minus c squared p squared equals 0. And of course, this looks pretty familiar. E squared equals c squared p squared plus m squared c to the 4th. And so you look at that and you go, well, God damn it, I knew that already, right? What did we go through all of this work to do all this, you know? It's like it leads to this trivial equation that we already knew from the beginning. And so you might think that this is just trivial. It's like, okay, who cares, you know? But it's not trivial. It turns out it's very profound. And what's profound is this. The profound thing is that we get, you know, and this was the beauty of Dirac. He just followed the math. He made no assumptions. He just said, what does the math tell me? And he really respected the math. And he said, this tells me that E is equal to plus or minus square root of c squared p squared plus m squared c to the 4th. And so that means that I have positive energy solutions and negative energy solutions. So that means we have positive solutions and negative solutions, negative energy solutions. And that's something new. That is new because we're talking about negative energy, because the thing is, we're talking about what the hell does negative energy mean? it actually is totally confusing, because remember, we're talking about a free particle. And so, you know, that means that the energy is equal to the kinetic energy plus the rest mass, right? Energy is kinetic energy plus rest mass. How the hell can that be negative? I'll just write that down.
Professor,
Yeah.
I don't see how this falls out of the Dirac equation though, because this is what we started with. This is the assumption we plugged into the Dirac equation.
Well, but when we, not exactly, because that's the thing, it's a subtle point. We started with this, right? When you write down this equation, you know, this equation, you know, E squared equals P squared C squared plus M squared C to the fourth. You write that down, and you've written it down 100 times, right? It's familiar. Yes?
Yeah.
Okay. And so that energy here is equal to kinetic energy plus rest mass. Is that a true statement? Yes or no?
Yes.
Okay. You've written that equation down 100 times. You know that it's kinetic energy plus rest mass. Can it be negative? Have you ever in your whole life thought that it could be negative? Yes or no?
No.
Correct. No. Neither you nor anyone else in the world ever thought it could be negative. Why? Because that makes no fucking sense, right? What the hell? Kinetic energy and rest mass add up to a negative number? It makes no sense. And so that's why when you use this equation in the past, you always just use the positive solution. You never thought that there's a negative solution. And so the difference now is that we're solving for the eigenenergies of a new Schrodinger equation. And we're not making any assumptions about sign. And we notice that when we go through the determinant and we get this characteristic equation, we get two different eigenvalues. One is positive and one is negative. And what Dirac did not do, he did not throw away the negative solution. He kept it. Do you see what I'm saying? That's the new thing. Do you see that?
Yeah.
And what is the significance of that, of keeping the negative energy solution? That gives us antiparticles. And by keeping that solution, Dirac became historically famous and got a Nobel Prize, all right? So he kept the negative energy solution. What you did not do, you wouldn't have thought of doing that. You would have thrown it away, and so you would not have gotten the Nobel Prize. But Dirac kept it, and therefore he discovered antiparticles and got a Nobel Prize. You see the difference? That's the difference between you and Dirac. Although, you know, maybe you'll discover something else even more important, who knows? But I just want you to see, you know, it's like, it's so subtle. I think it's just, to me, it's just really a funny, cute thing. It's like, you know, like I would have never thought to keep the negative solution. I would have said, that's crazy. And I would have just, you know, ignored that part. But Dirac did not ignore it. Okay, so we got these two solutions, positive and negative energy. And that negative energy solution is completely confusing and makes absolutely no sense. But Dirac said, the math gives me a negative energy solution, and therefore the negative energy solution is meaningful because Dirac believed in math. He was, you know, Dirac really respected the math. Dirac loved math. He really did. Dirac is basically the inspiration for, you know, string theorists, right? You know, all these theorists, he's like their hero. Okay, and so let's keep going. So then what is the consequence? What is the consequence of these solutions, E greater than 0 and E negative 0 solutions? Well, to find the consequence, let's do something. Let's find the eigenstates. How do you find eigenstates? Somebody remind me. What do we do next?
you basically set H operator, you acted on the psi and then set it equal to the value that we found times psi.
Okay, let's go back, because this is just a standard eigenvalue, eigenstate problem. So we go back to this equation. I'll give it 3 stars, right? We got our eigenvalues by setting that matrix equal to 0, the determinant of it equal to 0. Now we want to get our eigenstates. So to get our eigenstates, we got this gigantic 4x4 matrix that you're looking at right there. And what do I do to get my eigenstates? What do I do? Say it again.
Basically substitute the energy eigenvalues that we found back into that matrix and solve for A1 through 4.
That's exactly right. That's exactly right. So plug eigenvalues in. Plug the eigenvalues into it and solve for A1 through A4. Actually, it's a bad way to do it. A1, A2, A3, A4. That's exactly right. So we plug our eigenvalues into it and we solve, okay? And that's what we're going to do. So find eigenstates. So plug, and now I'll call the solutions E plus and E minus, okay? That's the positive one, plus square root, and this one is the negative one, negative square root. Okay, so I got the positive and negative solutions. Let's plug them into matrix above and find A1, A2, A3, A4. Okay, so we do that. Now, I'm not going to go through that math because it's quite tedious, but it's not hard. It's not hard. It's just a bunch of tedious algebra, but I'm not going to do it. I suggest that you guys go do it, you know, because this is historically important and leads to the discovery of antiparticles. I mean, geez, it's pretty, and also spin, the discovery, you know, this is the theoretical basis of spin. So, let's do that. And when you do it, then after a bunch of algebra that I'm not going to show, then you find the solutions. And I'm going to show you what the solutions look like. And you could figure it out. I mean, this is not beyond you guys. This is not like, you know, crazy, amazing, you know, math. You could really do it. To find the solutions, let's do this. Because, you know, it's very tedious to write all these things out. So let's define this vector, a 2-dimensional vector. And I'm going to call it up, the up vector, okay? And now I'm going to also define a down vector. And you know what these are going to end up being, right? Can you guess? It'll be spin up and spin down. Okay, but right now we have not invented spin. This is just math. I'm just taking the 1, 0 vector and just calling it up, and I'm taking the 0, 1 vector and I'm calling it down. But we haven't like discovered spin yet. You know, this is just purely math. And this is just a shorthand, because what I'm going to do is for the E plus solutions. So let's look at the positive energy solutions. For the positive energy solutions, E plus is equal to plus square root of P squared C squared plus M squared C to the 4. And for these solutions, we see that we get, because it's a 4x4 matrix, how many eigenstates are there going to be? Tell me.
4.
That's right, 4. You guys know that from linear algebra, right? And so I have 2 eigenvalues, but I'm going to have, but you know, there's got to be 4 eigenstates. So how many eigenstates are there going to be for each eigenvalue?
2.
Right. And do they have the same energy? Yes or no?
Yeah, they'd have to have the same energy.
Right, because they both are attached to the same eigenvalue. They're called degenerate. They're degenerate eigenstates. That's right. So I'm going to have two degenerate eigenstates by the rules of linear algebra. This is just math. And this is what those eigenstates look like. I'm going to call them, they're the positive energy, so that's where the plus comes from. And so they'll be state 1. It's going to be some constant in front. And this is the shape of the eigenstate. It looks like this. Here, it's a four vector, right? I mean, it's a 4-dimensional vector. So 2 of the dimensions are just going to be that simple one, 1, 0. But then I'm going to have these other 2 dimensions are a little bit more complicated. I'm going to have C sigma dot P over E plus MC squared. And this is a very compact notation, times up. Okay, so time, and then this whole state gets multiplied by it's a plane wave state. So that's going to be, because remember the wave function was A1 through A2. I mean A1. Remember that psi is equal to A1, A2, A3, A4 times e to the I k dot r. So that was the, remember, I'm putting the plane wave back in to get me my wave function. So that's the first state. And then the second state will be psi 2 plus is equal to, maybe I'll put little vector signs over it. Actually, maybe I won't. That's just getting to be too messy. Okay, then the other one is going to be this. It's going to be some constant times and here I'll put, it'll be down. And then here it's going to be C times sigma dot P over E plus MC squared times down. Okay, so those are the 2 4 vectors for the positive energy solution. And you can see it's pretty complicated. This is not simple. They're complicated because look at that bottom part. Those bottom 2 components are complicated because you got that, you know, I'm writing in a very compact notation, but these are actually sort of, you know, complex objects because remember, you know, don't forget, you know, sigma is equal to sigma x, a 2 by 2 matrix times x hat plus sigma y, y hat plus sigma z, z hat, where these are, you know, 2 by 2 matrices, right? So it's kind of a, that bottom part is sort of a complex object, but I'm writing it in this very clever compact notation because I don't want to write all that shit out. It's just too much. Okay, and so now what we're going to do is we're going to do something very clever because remember this whole this whole treatment is a combination of special relativity and quantum mechanics, and so this works for very fast moving particles going close to the speed of light. You know, they're very relativistic. This is a relativistic treatment of quantum mechanics, but let's remember that in the real, you know, in the real world, most of the time, well, I'll just ask you, are particles relativistic most of the time? Yes or no? Like when you're walking around in the street, you know, and you're eating your breakfast and watching your television, are all the particles in your life relativistic, yes or no?
I think so, right?
What?
I don't think most of them are relativistic since they would be moving at like a thermal velocity.
Exactly. They're not relativistic. Like when you're eating your ice cream, is that relativistic? No. When you're petting your dog, is your dog relativistic? No. When you open the window, is the window relativistic? No. Most things are not relativistic, you know? Like light is, you know, little particles of light, but I'm not talking about particles of light. I'm talking about electrons. We're talking about electrons, you know, matter, molecules, stuff in your, you know, the pencil in your hand. It's not relativistic. It's just sitting there. Okay, so most things are not relativistic. Of course, they can be relativistic. We could always, you know, accelerate them, but most of the time we don't. You know, most of the time we don't like take our computer and our dog and our ice cream. We don't accelerate to the speed of light. We find that to be very inconvenient. So most of the time things are not relativistic. So let's take, so since most of our world is non-relativistic matter, let's take the non-relativistic limit of this theory and see where it leads. So let's take the non-relativistic limit. What is the non-relativistic limit? What does that even mean?
Like when velocity is much less than c.
That's right. And so if I have, in the non-relativistic limit, what is this quantity? P over E goes to what? I mean, to make the units right, let's call it C times P. PC over E equals what in the non-relativistic limit? Actually, before you answer that question, tell me what E is in the non-relativistic limit. It's almost a trick question, but what is E in the non-relativistic limit? And let me remind you that E squared equals P squared C squared plus M squared C to the fourth. What is E in the non-relativistic limit? Tell me.
Would it just be the classical kinetic energy?
No, but that's a good guess. That's a good guess. That's a very reasonable guess, but it's not right. Look at this equation and think, what is this equation? What is this in the non-relativistic limit? What does that even mean? What is the non-relativistic limit? What does that even mean?
It's just MC squared.
What is MC squared?
The energy in the
Yes.
non-relativistic.
Exactly. E equals MC squared. That is the non-relativistic limit. Because what the non-relativistic limit means is that your kinetic energy is way smaller than your rest mass. Okay, that is the non-relativistic limit. So you guys, most of you guys forgot that, but you know, because you're not doing relativity all the time. But now you remember, now that I tell you. Now that I remind you, you remember, and then the one guy knew it. So in the non-relativistic limit, what that means is that your kinetic energy is tiny compared to your rest mass. Now in the ultra-relativistic limit, your kinetic energy can be 1,000,000 times more than your rest mass. Your kinetic energy can be gigantic in the relativistic limit. You can go so fast that the kinetic energy is 1,000,000,000,000 times bigger than the rest mass. I mean, think about it. Like, what about at CERN? You know, you have an electron, like at CERN, they have, you know, gigavolt. What is it? I can't even remember. I'm not a high energy guy, but you know, they accelerate things up to gigavolt. So if I took an electron and accelerated it up to a gigavolt, then that means that my kinetic energy is like 1,000 times more than my rest mass. So okay, that's the ultra-relativistic limit. But in the non-relativistic limit, the kinetic energy is negligible compared to the rest mass, and so this part goes away. In the non-relativistic limit, this part goes away, and E equals MC squared. Okay, so I have, in the non-relativistic limit, E is MC squared. So now let's get back to that question. What is the ratio of CP over E? That's the same as the ratio of CP over MC squared. What is that ratio in the non-relativistic limit?
It goes to 0.
Yes, exactly. So in the non-relativistic limit, now let's go to our solutions. What does this factor equal in the non-relativistic limit? Tell me.
0.
Yes. In the non-relativistic limit. Zero in non-relativistic limit. So in the non-relativistic limit, my wave function is really simple. I'm going to just set those guys to 0. In the non-relativistic limit, which is the limit where most of the physics happens in our day-to-day life. In the non-relativistic limit, we have for E is equal to positive square root of P squared C squared plus M squared C to the fourth plus m squared c to the fourth. Then I'm going to have psi 1 for that positive energy solution will be, it's going to be that spin up. Spin up is 1, 0, right? That's what this guy is. You know, he's 1, 0, right? And then what are these other two guys on the bottom going to be? What are they? Tell me.
0.
Yes. 0, 0. E to the I k dot r. And psi 2 plus is equal to, let's go back up here. It's going to be spin down, that down vector, which is 0, 1. And what are these two guys below them going to be?
Also 0.
That's right. 1, 0, 0, e to the I k dot r. That is the wave function. That is the free particle wave function, the non-relativistic limit. Now, we don't have to worry about, so this is the non-relativistic positive energy solution. And does this look familiar? Does it? It should. What does it remind you of? What is it?
Basically, it just seems like it's like a free particle with either spin up or spin down.
Yeah, you've dealt with this before. This is just a normal plane wave with spin. Because you just basically have psi plus is equal to e to the I k dot r up, and you have psi minus is equal to e to the I k dot r minus down. You've done this a million times, so you've seen this before. So we just, but we derived it, you know, we derived spin. So I think, you know, so at this point, you're, you know, I mean, we derived spin. I don't know what more to say, you know, like what we did was we just, starting from the solution that the Hamiltonian is proportional to momentum, we just derived spin. And it's such a subtle, tricky little argument that you guys might not even have realized what we have just done. But we just derived spin from nothing, you know, we're just using our brain, just using the assumption that the Hamiltonian is proportional to momentum in order to create, in order to put space and time on the same footing. That can only work if spin exists. So that's like really freaky. We just invented spin. We derived it. Although it's just such a subtle argument that it might have just like slipped over you. You know, it's like at this point, you know, we're just following the math, and suddenly, boom, there's spin. So we just invented spin. Okay, because we, you know, so, but let's keep going because there's more to be invented than just spin. So now,
Can I ask a question about spin before we go on?
Of course.
So this is like great for like 2D spin, like either up or down. But like there are like particles we did with like that had different amounts of spin. Like where does that come from?
That's a great question. That's a great question because remember how I said that alpha and beta are 4x4 matrices, and these are the simplest solutions to the constraints that we derived last lecture? I mean, these are the constraints. Where are our constraints? Here they are. This is the starting point of everything right here. I'm circling it. Remember, we got constraints to alpha and beta by setting these two guys, you know, the e squared psi is equal to h squared, and we expanded it out, and we got, remember, we got the anti-commutators equal to 0, right? Or I don't know if you remember that from last time.
Yeah.
Okay, and then we said, and then what I said was the simplest solution to those anti-commutators is a 4x4 matrix, right? Well, the 4x4 matrix is for spin 1/2. But what happens if, but then I can ask, well, what's the next simplest solution? Because there's a whole infinity of solutions to those constraints. And so the next one will be instead of a 4x4 matrix, it's going to be a, I can't remember, but it's like a, you know, like a 9x9 matrix or something. You see what I'm saying? And then the next one
Right.
after that will be a 14x14 matrix, and then there'll be a 17x17 matrix. And what the hell are those solutions? What do they correspond to? Can you guess?
Higher numbers of higher spin numbers.
Yes. Yes. See? So it all fits together. Click, click, click. It all fits together like a little Swiss watch. Okay. So isn't that cool? But this
It's
is
really cool.
Yeah, it's very cool. It's the Dirac equation is amazing. I mean, once you start really appreciating it, you're like, oh my God, it's so simple. Well, it's not that simple. I mean, because look, let's go back to these solutions. You know, these are the relativistic solutions. That's pretty complicated. You know, getting an intuitive feel for the relativistic solutions is quite tricky. But let's still stick with the non-relativistic solutions. So those are the positive energy solutions. Now let's do the negative energy solutions. The negative energy solutions for the non-relativistic limit are going to be this. You can already guess. So let's not go through all the math. I'm going to skip all the math, but I'm going to jump right to the solution. And for the negative energy solutions, what's going to happen is the whole structure is going to be flipped on its head. For the negative energy solutions, see how I have that, I'm drawing a little, see, well, for the negative energy solutions, actually, let's just, you know, for the negative energy solutions, I'm going to have psi is equal to, you know, I'm going to have this, I'm going to have my C sigma dot P times spin up over E plus MC squared or whatever it is. And then I'm going to have my, my spin up. You see, I'm going to have this part on the top. You see? For the negative energy solutions. I'm going to have it, and then I'm going to have the same thing, you know, I have that on the top. And so when I go through all the arguments, my negative energy solution, my first negative energy solution is going to be equal to a four vector times the plane wave. What do you think that 4 vector is going to look like? Tell me.
0, 0, 1, 0.
0, 0, 1, 0. Exactly. And what do you think my second negative solution is going to look like? I'm going to have a 4 vector times a plane wave. What is it going to look like? Somebody tell me.
0, 0, 0, 1.
That's exactly right. And so basically, that's what it is. And so you can see that this is going to be spin up, and this is going to be spin down. So I get 2 solutions. But these solutions, notice it's in a whole different dimension. You know, these are orthogonal solutions. These solutions these are orthogonal eigenstates. These are orthogonal to the positive energy solutions. So I'll just say orthogonal to the positive energy solutions. These are new solutions. So these are the negative energy solutions. So I have negative energy spin up and negative energy spin down. Okay? The math is very simple. It just, that's what it is, right? So these are the negative energy solutions. Negative energy solutions. Okay? And the math is very simple and very obvious. So even in the non-relativistic limit, I have positive energy solutions and negative energy solutions. And I have spin up and I have spin down. We just derived that. But what does it mean? Let's keep going. What does it mean? So what it means is, look, let's write it all down. I mean, I have E plus minus is equal to plus minus square root of P squared C squared plus M squared C to the 4, where this P is equal to H bar K, right? So that means that this is, I can write this as h bar squared k squared c squared plus m squared c to the 4. So let's plot this. Let's plot E versus K. Plot it. Let's plot E versus K, or just plot this function. I'm just going to plot this function. And when we plot that function, it looks like this. E, K, some funky parabolic looking kind of thing. It looks like this. And this is plus mc squared, and this is minus mc squared. And that's it. So those are the free particle eigenenergies. I've got these are the positive energy ones, and these are the negative energy ones. And so Dirac said, this is what it's got to be. These are the solutions. This is how quantum mechanics must work. There's got to be positive energy solutions and negative energy solutions. Now, the positive energy solutions make sense. You see how it's offset from 0 just by the rest mass. That is not confusing because, you know, basically we have kinetic energy plus rest mass, you know, because energy is equal to kinetic energy plus rest mass. So this top curve is very sensible and it looks normal. It makes a lot of sense to us. But it's the bottom curve that makes no goddamn sense. The bottom curve makes no goddamn sense. And so, but Dirac said, look, the math says that this is true, so it's got to be true. And so you start looking at it, and so Dirac started looking at that, and Dirac started thinking, okay, there's a problem. What's the problem? The problem is this. If I put a particle into a positive energy solution, this is E, this is K. Suppose my particle is right here, okay? The particle is, suppose I have a particle occupying that state right here. Now, that's an eigenstate. It's a stationary solution. So will that particle change in time? Yes or no? Does it change in time? It's a stationary state. What's the definition of a stationary state?
It doesn't evolve in time.
Right. It just has a, you know, a phase factor, e to the negative I e t over h bar, the phase factor, but it doesn't really change in time other than that just simple phase oscillating. That's right. It just sticks there, stays there. It's an eigenstate. But now in this class, you learn perturbation. You know about perturbation. So now, because we talk about perturbation theory, so now let's perturb it, okay? Let's shine light on it. Let's do something. Let's perturb it. And that's going to cause a transition. So now it can decay because I'm perturbing it. It's the perturbations that cause the decay. So now let's perturb that. And what is that state going to do? What's it going to do? Tell me.
Oscillate.
It could do that, but you know, when you have an atom and you have an atom in an excited state and you shine light on it,
Oh, it'll just fall back down. It'll just fall back down.
Exactly, it's just going to fall down. But look, notice that this can fall all the way down to the negative energy. And once it goes here, it can keep on falling. You see that? It can fall all the way down to hell, all the way to hell. And the devil is down there in hell and he catches it in his mouth. All right, so it falls all the way down into the devil's mouth, all the way down into hell. And that means that that electron that fell all the way to hell is going to emit the energy. It's going to emit a photon. What will be the energy of that photon? The devil catches it in his mouth, and right when he catches it, it emits a photon. What's the energy of that photon? Tell me. The electron fell all the way to hell.
Infinite?
Yes, exactly. Infinite. It'll emit a photon that has infinite energy. So does that make sense? I mean, you're made out of electrons, right? That's what you're made out of, protons and electrons, molecules, everything around you, you're made out of electrons. And so that means that those electrons, each one of those electrons can fall because you are being perturbed all the time. Light is being shined on you, from the sun. So that means that all your electrons could fall all the way down to hell, right? And emit photons of infinite energy. Does that happen? Look around you. Does that happen? The answer, of course, is no, it doesn't happen. So this is a problem. And Dirac recognized this. He said, oh my God, every electron can just fall all the way down, in energy, infinitely far, and emit photons of infinite energy. This makes absolutely no sense. This does not happen. It makes no sense. It's crazy. And so, but on the other hand, Dirac said, but my math is flawless, because the guy's so smart. He knows that his math is perfect, and he believes his math. And so he's faced with this paradox. And so how did he solve the paradox? Somebody tell me.
Antiparticles.
What does that mean?
Maybe there's all the states that are E less than 0 are already filled up, so you can't go there.
Exactly. That was the solution. He filled them up. He said all these states must be filled. Are those antiparticles, yes or no? Are those antiparticles, yes or no? Somebody answer the question.
No.
Correct. They are not. They are negative energy particles. They are not antiparticles. And we have a name for this. It's a whole sea of particles, a sea of negative energy particles, a sea of negative energy particles. What do we call the sea of negative energy particles? It has a name. What do we call it? We call it the what?
Dirac Sea.
Yeah. We call this the Dirac Sea. It's the Dirac Sea of negative energy particles. They are not antiparticles. They are not antiparticles. They are not antiparticles. But we're going to get to antiparticles in just a minute. But first, let's just appreciate this picture. So Dirac said, okay, I have these negative energy solutions, but I noticed that particles don't fall, and emit, infinite energy photons. It doesn't happen. Otherwise, the whole universe would just explode, in an instantaneous moment, we would just all explode. And so that doesn't happen. So then those states must be filled. And that's why we don't fall all the way down. But he said, but my math is flawless. And so those states must exist. The Dirac Sea must exist. It's got to be there. And if it's there, then that means we should be able to observe it. How can we observe it? How can we observe the reality of the Dirac Sea? Now, I cannot fall into the Dirac Sea because the states are filled. I can't go into those states. But what could I do instead? What could I do instead?
Excite one of the negative energy states.
Exactly. How much energy do I need to do that?
Two MC squared.
That is exactly right. That is right. So look, this state right here at the bottom, right here, the topmost negative energy state with the most positive, with the highest energy, you notice that to excite that up into the positive energy regime, I need to overcome this energy gap. This energy gap is 2 mc squared. Now, what is mc squared? That is the rest. So suppose these are we're talking about electrons. And so what's 2 mc squared? Can somebody tell me? What is mc squared for an electron? Does anybody remember? I don't even think I remember. Does anybody remember? Come on, just one of you guys must be like a budding high energy person. Does anybody remember what is the rest mass of an electron in electron volts?
I think it's like 0.511
0.511 what?
mega electron volts.
Exactly. It's like 500,000 electron volts. That's right. And so 2 mc squared is 1,000,000 electron volts, right? So delta E is like 10 to the 6 electron volts. And so what Dirac then predicted is that means that if I have a photon that has an energy of 10 to the 6 electron volts, then that photon, if it can give its energy to one of these negative energy electrons, it can excite it up to here and leave behind a hole in the negative energy C. That's what he predicted. Now, what is this hole? That the hole that gets left behind, what is that? What do we call the hole that got left behind? What is that called?
Antiparticle.
What?
An antiparticle.
Yes. That is the antiparticle. And so this hole has, if you have a filled band of negatively charged particles, because they're electrons, they're negative. We're talking about electrons, and so these are all electrons, negative energy electrons. But if I pull one of them away, then what I'm left behind is a hole, and that hole acts as though it has positive. It has positive charge. It acts like a positively charged particle. And that might not be obvious to you, but if you think about it, it is obvious, but it takes a while to think about it. This is like very standard condensed matter physics kind of thinking, because if you have a semiconductor and you have the filled valence states and you pull an electron out of the valence states of silicon, you're left behind with a hole, a positively charged particle in the silicon. This is very common from semiconductor physics. Probably most of you might not know that, but if you take solid state physics, you'll learn about that, because in silicon you have electrons and holes, you have n-doped and p-doped, all of that stuff. This is exactly the same thing. So it's the same reasoning, but I don't have time to get into all those details. So it's positively charged particle. And that, the hole, not a zero, it's a hole, is a positively charged particle. And that we call a positron, right? And so Dirac predicted the positron, and he predicted this. Dirac went through all this reasoning. And he said those states are filled, but that means if I have a high energy photon, I should be able to create a hole, and that means that a photon gamma should be able to go and create an electron E minus plus a hole, E plus. So it's basically this, gamma goes to E plus. This very famous high energy reaction. A high energy photon should be able to create an electron hole pair. Electron, positron pair. So that was what he predicted. He predicted that a photon, boo, 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 should be able to create an electron and a positron. I'm not even sure I'm drawing that correct. It's like a Feynman diagram. I never do Feynman diagrams. I'm not sure I'm drawing it correct, but I think that's how you draw it. But this is what he predicted. This is a photon can turn into an electron. So basically he predicted that a photon, a ray of light, could just spontaneously turn into an electron and a positron. I mean, that's absolutely freaky. He predicted it. And then everybody thought he was crazy until in 1932, this guy whose name is Carl Anderson, like in the Matrix, Mr. Anderson. Carl Anderson, he invented the cloud chamber, and he saw positrons. Okay, so everybody laughed at Dirac and thought he was kind of crazy for saying all this until this dude actually saw it happen. It actually happened. The photon turned into an electron, and then this other very strange particle, a positively charged electron. So Carl Anderson saw a photon spontaneously turn into an electron, a negatively charged electron, and then a positively charged electron. And that was absolutely freaky, but it showed that Dirac was right. Okay, so that's pretty cool. And so that's pretty cool. That's the discovery of antiparticles. And the thing that I think is so amusing about this whole thing is that it all just comes. It's like all that Dirac did was assume that the Hamiltonian is proportional to momentum, and you just make that trivial assumption in order to get time and space on the same footing, and boom, out pops spin, out pops antiparticles with the correct mass. And there's even more that pops out. So the next thing that pops out, one other thing pops out of this equation, which is the fact that the next thing that popped out is the fact that spin leads to a dipole moment. A charged particle with spin if a particle has spin, then that charged particle has a magnetic moment, G Q over 2m times S. This is the magnetic moment of a charged particle with spin. You have seen this equation. This leads to the Zeman effect that you guys have used already, but no one ever told you, why does a charged particle with spin have a magnetic moment? Well, it turns out that it comes out of the Dirac equation. And so I'm going to derive that right now, actually. And so this is going to go over, so it's 11:52 right now. And this last thing that I can derive, it will take me about, I don't know, it'll take me like 15 minutes to derive, but I'm just going to do it. And if you guys have to leave, then just leave and you can look at the recording or not. It doesn't matter. This will not be on the final. But since we've gotten this far, I figure I'll just finish it off and I'll derive, because this is the G factor. That's the famous G factor. What is the G factor equal to? Somebody tell me. For an electron.
2.
That's right. So an electron with spin has a magnetic moment, which is already sort of strange. Why does that happen? And the magnetic moment is equal to this factor I just wrote there, and the G factor is 2. We can derive both of those things from the Dirac equation, and it's really simple. It's just like it's like 2 pages of algebra. So let's do that. But of course, I realize that this is going to go over. I'm going to go a few minutes, I'm going to go like 10 minutes over. So, if you got to leave, just leave. And you can look at the recording or not, whatever. But I just think, since we've come this far, might as well just take that. It's just one small extra step, to get the magnetic dipole and the G factor. I mean, why not, So because it's like just, to me, it's just so extraordinary that all this stuff comes out of this very trivial Dirac equation. So let's do it. So let's do this. So let's derive the magnetic moment and G factor for electron. Let's derive it. And so to do that, let's solve the Dirac equation in a magnetic field. All right? And to do the Dirac equation of magnetic field, to do quantum mechanics in a magnetic field is slightly tricky. Because remember, magnetic fields don't change the energy of a particle. And so writing down the Hamiltonian is sort of not trivial, but there's a trick, and I actually mentioned it in class. But the trick in quantum mechanics, the way that you introduce magnetic fields in quantum mechanics is you take the momentum of the particle and you replace that momentum with what? And this is this is classical. This is the classical Hamiltonian. This is a classical mechanics result. Although we give short shrift to classical mechanics these days, we kind of don't. Most students aren't taught this too well. But in classical mechanics, how do you introduce magnetic fields into your classical Hamiltonian? Does anybody remember? Momentum turns into what? Does anybody remember? Does it even sound vaguely familiar? I mean, look, I realize you might not remember, but have any of you even seen this in a class ever? Like, does this even look vaguely familiar to any of
We
you?
have to add the vector potential, right? Like times the charge.
Perfect, thank you. That's cool. Okay, so some of you have seen it, right? So the momentum it's like the canonical momentum, all that fancy Hamiltonian Lagrangian stuff. So you take the momentum and you replace it with P minus QA, where that's the vector potential, where the magnetic field is equal to the gradient cross del cross A. And that's a very famous result from E&M. So if you've taken 110A, then this should look very familiar to you. But this is how you introduce magnetic fields into quantum mechanics. And so that means that for an electron in a B field, then let's solve the Schrodinger equation. And the Schrodinger equation is H psi equals E psi. So let's solve it. But it's not the Schrodinger equation anymore. Now it's the Dirac equation. So let's solve the Dirac equation for this. And so basically what we have is H psi, but psi is psi 1, psi 2, psi 3, psi 4 is equal to E. It's the Dirac equation, right? So I got this 4-component object, wave function. And so what we do is we have this, and we have the Hamiltonian. Now the Hamiltonian is going to be C times alpha dot P, but now P gets replaced by this new momentum, P minus QA, plus beta MC squared. Okay, so that's my Hamiltonian. And so now I want to solve H psi equals E psi with that Hamiltonian. So let's solve the Dirac equation. So to do it, I'm going to use compact notation, because the algebra is quite tedious, but we're going to introduce compact notation. And the compact notation is that alpha can be written as 0 sigma, sigma 0. I already introduced that before. And my wave function, psi, is going to be, I'm going to call psi, I'm going to take the positive energy solutions and call them chi, and the negative energy solutions and call them phi, where chi, chi is equal to psi 1, psi 2, and phi is going to be equal to psi 3, psi 4. Okay, so I'm sort of going to write it in this more compact notation. And so then if I write H psi equals E psi and plug these things in using the compact notation, then I can write my equation in this sort of simpler way. I can write it like this. I can write it as C times P minus E. Oh shoot, did I get this sign wrong? I think this is plus. I'm sorry, I'm getting this think that this is plus QA, not minus. My notes have a little inconsistency here. How did I get this? Oh, no. God damn it. Sorry, I just want to P minus QA. Yeah, okay, P. Sorry, I just have a little error in my notes here. P minus QA dot 0 sigma 0 chi phi plus mc squared times I 0 minus I chi phi is equal to E chi phi. Okay, so that's the Dirac equation. I just reversed the order because these operators commute. They commute. So it's okay for me to do P dot alpha instead of alpha dot P. So I just reversed the order there, but that's okay because they commute. And so that's the Dirac equation. So this is just H psi equals E psi. And I'm going to rewrite this. And what I'm going to do now is I'm going to manipulate this equation, and suddenly, magically, out will pop the magnetic moment and the G factor. It's almost like a miracle, but it's really simple. So let's solve this. And so what I'm going to do is let's do the. I can break this into two equations. So I have a top. I have the top and bottom. So that means I can break this into two equations because the tops are all equal and the bottoms are equal. It's just that, you know, this is just linear algebra. So let's do the top part. So if I do the top part, then I'm going to get C. So let's do the top, and I'm going to get C times P minus QA dot sigma times phi plus mc squared chi is equal to E chi. So do you see how I got that? I just did the top part. I mean, can you guys see that? Okay, you know, because the top part is like this part, right? You know, that's the top part. And I just did the matrix, you know, multiplication for the top part. And now I'm going to do the bottom. And the bottom is going to be C times, let me make sure I got that right, yeah. C times P minus QA dot sigma chi plus negative mc squared phi is equal to E phi. Okay, so that's the bottom. So I just broke it up into two equations. And so now what I'm going to do, so now I have two equations. So now I'm going to play a little trick. It's not that hard. I'm going to take this equation and solve it. And when I solve it, I'm going to solve for phi. And it's really easy to see that it's just C times P minus QA dot sigma divided by E plus mc squared. Okay, I just want you to see that there's nothing tricky here. So I just solved for phi from that bottom equation. Does that look right to you guys? Did I get that right? No, I left out a chi. Okay, does that look right?
Yeah.
Okay, good. So now what I can do is I can take this and I can plug it in. to here. Plug it in. And so then when I plug it in for phi, you see I'm going to plug it in right here, okay? So when I plug it in, it's going to look like this. C times P minus QA dot sigma. And now I'm going to plug in for phi. It's going to be C times P minus QA dot sigma over E plus MC squared chi plus MC squared chi equals E chi. Okay, does that look okay, folks? Does it look okay? Just say yes.
Yeah.
Okay, so that looks okay, good. So now let's take the non-relativistic limit. Which means that E goes to MC squared. So this guy right here, that guy's going to go to MC squared. So now you see that on the bottom of that denominator, I'm going to get 2 MC squared. But because I have these 2 C's here, and here, and they're going to cancel with these C squareds here and here. You see they cancel. And so when I do that non-relativistic limit, then that equation is going to turn into this. It's going to turn into P minus QA dot sigma squared over 2m, because the C's went away, times chi equals E minus MC squared, because I grouped the terms, times chi. Okay, do you see that? All right. So nothing fancy here. I haven't done any tricks yet, but I'm about to. So this is the non-relativistic limit. And so now, okay, now comes the fancy math trick. Fancy math trick. And there's some tricky little math here that I'm not going to go through because it's just tedious and too much algebra and stuff. But this is the math trick. It turns out that there's an identity that we will use. A dot sigma B dot sigma is equal to A dot B plus I sigma dot A cross B. And this is for sigma equals the Pauli matrices. Okay, this is a fancy math trick. And I'm not going to derive this math trick, and I'm not even going to plug it in and show, go through all the details. But you'll just have to take it on faith, okay? And you guys can like look it up and try to figure that out. I think if you look in Lieboff, the book by Lieboff, he has a problem on this, which I think talks about it, problem 11.101 in the Lieboff book. Okay, but using this trick, then this equation reduces to this, and so this is the step I'm going to skip, but the equation reduces to this. I have 1 over 2m P minus QA squared chi minus IQ over 2m sigma dot P cross A times chi is equal to E minus MC squared chi. Okay? So that's the step that I'm skipping. It's just, but it's math. It's like no fancy physics, just math. But now we have this, and so now we're going to notice something. Let's notice this. Let's notice that this part, P cross A, is equal to H bar over I del cross A equals H bar over I times what? Somebody tell me. Somebody tell me.
B.
Exactly, B. That's right. So plug it in there. So plug it in. And then what we're going to get when you plug it in, we're going to get 1 over 2m P minus QA squared chi minus QH bar over 2m sigma dot B chi is equal to E minus MC squared chi. Okay, and so now let's change the notation. Let's just rearrange the notation. Let's call, let's take this H bar over 2 sigma, which appears here, and let's call it, can you guess? What are we going to call that? What's H bar over 2 times sigma? What is it?
In matrix.
Yeah,
It's the what?
the spin matrix.
Right. Let's call it operator, spin operator. That's right, S. Let's take one of these factors of, let's take a factor of 2, and let's define this new variable g, that we'll call it, and let's define this, let's just define a factor g and call it 2, all right? This is a definition. And let's define a new operator, mu, which is equal to gq over 2m times s, where g is 2. So these are definitions. These are just, let's just define these. We're just defining these new terms. We're just changing the notation. But with this new notation, let's plug it in. Let's plug in the new notation. And what do we get? We get this. 1 over 2m P minus QA squared minus G Q, oh no, I'm sorry. Minus mu dot B chi is equal to E minus MC squared chi. We did it. That's the end. We just derived it. It's like very sneaky. It's a sneaky little derivation, but you realize that what we've just derived is the Zeman term. We just realized by going through the math, you realize that in the Hamiltonian, if you rearrange the Hamiltonian, you realize that the Dirac equation in the magnetic field gives you this new energy term, which is mu dot B. It's a new term in the Hamiltonian, a new energy term that you've never seen before. I mean, you have seen it before, but you've never derived it. A new energy term. But we just derived the Zeman energy. It's just such a sneaky little derivation. You're like, wait, how'd that happen? But we just derived the fact that we have a magnetic moment, which is equal to G Q over 2m S. And we also derived the Zeeman term is negative mu dot B, where mu is that. And so we just basically derived the Zeeman term, we derived mu, and we derived the G factor. It all just pops right out. And that's it. And so all of this stuff, and it all just comes from, remember, all of this stuff comes from the fact that we just said, let's let the Hamiltonian, all we did to do all that was we just said, let's let the Hamiltonian be proportional to momentum so that space and time can be on the same footing. And we made that trivial assumption, and boom, we got antiparticles, we got spin, we got the G factor, we got the Zeman energy, and we got the magnetic moment of the electron. All of that stuff, just poof. So I love this. I love this derivation. It's just like magic. It's amazing. Okay, that's it. So we're done now. And so I guess that's it. The course is over. And I guess that's just, there's just the final left. And for the final, you know, I'm not into cumulative finals. So the final will just be emphasizing the stuff that came after the midterm. Okay, the stuff that's not on the midterm will be the final. And I will, and me and Newton are kind of, I'm gonna send you guys a bunch of information telling you, you know, how to do the final, and then you guys we can still discuss that. There'll still be a class tomorrow morning at 9 a.m. and you guys can ask me more questions about the final then. But even if you don't come to the Friday morning class, I will still send out, you know, emails and, you know, notices explaining how the final is going to work and all those details. And it should not be too bad. It'll be very similar to the midterm. And I think it'll be quite reasonable, I think, and, you know, it'll be okay. Okay, folks, any last questions? Okay, bye-bye.
Thank you.
All right.
Okay.
Thank you.
Thank you, Professor.
Okay.
Thank you so
bye-bye.
much.
Yeah, my pleasure.